Hello and welcome to the video for section 9.7 on Taylor polynomials and approximations. Our objectives for this video are number 1, find polynomial approximations for elementary functions. Number 2, find Taylor and Maclaurin polynomial approximations. And 3, use the remainder theorem of a Taylor polynomial. So let's start out with looking at a polynomial that we're going to use to an nth degree polynomial that we're going to use to approximate a function. Okay, so we're going to have p sub n of x is a0 plus a1 times x minus c plus a2 times x minus c squared. So all the way down to a sub n times x minus c to the n. So we have this nth degree polynomial and we're going to approximate f of x, and it's going to be centered at x equals c. So what this means in this case, we want to come up with a polynomial that is going to have the that we can use to approximate f of x, and we want it to be as good of an approximation as we can possibly get. So the main thing that happens when you're working on these things is that not only, when we plug in c, the first thing we're going to want is that when I take and I calculate f of c, I want that to equal the same value that I would get for the polynomial if I plugged in c, which in this case is a sub 0. Okay, so that's going to be the first thing. It would make sense that we would have to have that point in common, that c comma a sub 0 would have to be a point on the polynomial and on f of x for us to have a good approximation centered at x equals c. Now, the way we can get the better approximations, though, is by going through and matching derivatives. For example, one of the ways that we've gone in the past to approximate a function is to use a tangent line. Okay, so that would be really the tangent line is just going to be a first degree polynomial approximation of our function. And then when we had values that were close to our c value, our tangent line values and the function values would be fairly close as well. And again, as we move farther away from c in both directions, we're going to end up getting a more error. And so when we go through on that one, we can mitigate that error by going through and making it so that our polynomials, that the derivatives match up. So not only do we want, will we get a better approximation when f of c equals a0, but also if f prime of c is equal to the first derivative of p evaluated at c. If the second derivative is equal to the second derivative of our polynomial, and so forth, all the way down to the nth derivative is going to be equal to the nth derivative of p evaluated at c as well. If those when we have those, that's what's going to give us our best approximation. So now we're looking at our function f of x. And what you see here, we know that the polynomial, our nth degree polynomial, is going to be a0 plus a1 times x minus c plus a2 times x minus c squared. This is just what we had in the previous, on the previous slide for our polynomial. Okay, our first derivative of our polynomial is going to be a1 times 2a2 times x minus c times 3a3 times x minus c squared plus 4a4 times x minus c to the third, all the way down to n times a sub n times x minus c to the n minus 1. We're just using the power rule. Now I'm going to go and take the second derivative. So the second derivative of p is going to be 2a2. Remember, the derivative a1 is going to be 0. So I'll get 2a2 plus 6 times a3 times x minus c to the first, plus 12 times a4 times x minus c squared, all the way down to n times n minus 1 times a sub n times x minus c, and that's to the n minus 2 power. When I do my third derivative, I'll get the 6a3 plus 24a4 times x minus c to the first. Now I've added in this 68 to the fifth, a sub 5 times x minus c squared. You didn't see that one before, but added that one in for this purposes now. Plus all the way down to n times n minus 1 times n minus 2 a sub n times x minus c to the n minus 3 power. Now I take the fourth derivative. I get 24 a sub 4 plus 120 a sub 5 times x minus c to the first, and then it goes all the way down to n times n minus 1 times n minus 2 times n minus 3 a sub n times x minus c to the n minus 4. And finally, the fifth derivative is 120 to the fifth plus all the way down to n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times a sub n times x minus c to the n minus 5. So we have all this, okay? We have a lot of numbers there, a lot of things happening. We're just doing the power rule the whole time. But what we want here, we want at this point, what is the nth derivative going to look like? What's going to be the nth derivative? Well, the thing I want you to recognize here, let's look at these constant terms that we have. Look at the coefficients. The coefficient here is 1, coefficient 1, 2, 6, 24, 120. That pattern should be familiar to you right now. Okay? That pattern, if you should recognize it, that is actually going to be, this is, here we have at this, right here, it's the zero derivative. That is 0 factorial, 1 factorial, 2 factorial, 3 factorial. The fourth derivative, I have 4 factorial. The fifth derivative, I have 5 factorial. So when we get down to the nth derivative, it's going to be it's going to be n factorial times a sub n. And you kind of see that n factorial building with this. And if we keep going, we're going to end up with n times n minus 1 times n minus 2 all the way down until we get times 3 times 2 times 1. So what we have is this. Now the other thing that you have, remember on this one, we wanted the derivatives to be equal at x equals c. So I know in this case that f prime of c is going to equal a1. I know f double prime of c is going to be the value of the second derivative of c, which is going to be 2a2. Because all the things with the x minus c are going to drop off. They're going to be 0. I know the third derivative of f at c is going to end up being 6a3. I know the fourth derivative of f at c is going to be 24a4. And I know the fifth derivative at c is going to be 120a5, which we can now go through. Remember, the key thing is these particular constants. What are they equal to? Okay? Well, already I know that f of c is equal to a0. Okay? But in general, I know the nth derivative of f evaluated at c is going to be n factorial times a sub n. And from there, I get to my general statement. I solve this for a sub n, and I find a sub n is equal to the nth derivative of f evaluated at my center point all over n factorial. The coefficients that we see in our polynomial approximation will be equal to this expression right there. That a sub n, whatever a sub n is, a sub 1, a sub 2, a sub n is the nth derivative of f evaluated at c over n factorial. So now we're going to go through and rewrite that polynomial, but using our expressions that we now know for the coefficients of the a sub n's. And so what we have is, if f has n derivatives of x equals c, then the polynomial p sub n of x equals f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c to the third, all the way down to the nth derivative of f evaluated at c over n factorial times x minus c to the n. This is an nth degree Taylor polynomial for f, which is centered at c. Okay. Now, the other thing we have This is our general Taylor polynomial that we're going to use to approximate a function. We do have a special Taylor polynomial called a Maclaurin polynomial. The Maclaurin polynomial is one that's centered at c equals 0. So if we're looking at where we replace c with 0, what we're going to get is that the nth degree polynomial f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus plus the nth derivative of f evaluated at 0 over n factorial times x to the n. That is the nth degree Maclaurin polynomial. Notice we don't say Maclaurin polynomial centered at 0. By definition, a Maclaurin polynomial is always centered at 0. So now that we have this definition of a Taylor polynomial, Maclaurin polynomial, our next job is going to be to find one for a particular function that we're working with. So in this case, our first example we're going to look at is we're going to find a third degree Taylor polynomial for the natural log of x, but we're going to center it at x equals 1. Okay? So we know that that third degree polynomial is going to take the form of f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime of 1 over 3 factorial times x minus 1 to the third power. So this now gives us, this is a general form of our third degree Taylor polynomial for the natural log of x. And so what we need to do is we need to evaluate those. So the first thing I'm going to do is I'm going to identify our function and all the way up in this case to the third derivative. So for this particular problem, I have f of x equals the natural log of x. F prime of x is going to be 1 over x. The second derivative is going to be negative 1 over x squared. And the third derivative is going to come out to be 2 over x to the third power. And so I now need, the next thing I need to do is evaluate each one of these at x equals 1. So in this case, f prime of 1 is equal to 1. F of 1 equals 0. Okay, naturally 1 is 0. F prime of 1 equals 1. F double prime of 1 is negative 1. And f triple prime of 1 comes out to be 2. And so our third degree, we can now take that information and we can now write out our third degree polynomial. So P3 of x is going to be, I'll replace f of 1 with 0 plus f prime of 1 is 1 times x minus 1. F double prime of 1 is going to be 1 over, or negative 1, sorry, over 2 factorial times x minus 1 squared. And then plus f triple prime of 1 is 2 over 3 factorial times x minus 1 to the third. And so the last thing we want to do is simplify this. And if I simplify it, I get that P3 of x, that's 0, that's going to be equal to x minus 1 minus 1 over 2 factorial is 1 half times x minus 1 squared plus 2 goes in, we have 3 factorial is 6, so 2 goes into 6 3 times, so it's going to be 1/3 times x minus 1 to the third. Or if you want, you could say it's x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. That would be my third degree Taylor polynomial for the natural log of x centered at x equals 1. Pause the video right here. Make sure you're comfortable with what I did to get this particular polynomial. And then once you're ready, we can move on to our next example. So now in this example, we're going to find a fifth degree Maclaurin polynomial for y equals sine of x. Now, because remember, we're dealing with the Maclaurin polynomial, c is 0. So our general form for this polynomial, it's a fifth degree, so it's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared, f triple prime of 0 over 3 factorial x cubed plus the fourth derivative of f evaluated 0 over x to the fourth, and the same thing for the fifth derivative of f evaluated 0 over 5 factorial x to the fifth. So I've got to go through on this one, and I got to calculate these. And again, I'm going to do the same thing I did before, but this time I have to go to the fifth derivative. So for this particular problem, we know y equals sine of x. So I'm going to go through and say f of x equals sine of x. So I now need to go through and again take all the way up to the first derivative. So f prime of x is going to be cosine of x. F double prime of x is going to be negative sine x. The third derivative is going to be negative cosine x. The fourth derivative is going to be sine x. And the fifth derivative is going to be cosine of x. Now again, on this one, we're taking this as we're centering it at 0. So the next thing I have to do is I do have to go and evaluate each one of these derivatives at 0. So f of 0, in this case, the sine of 0 is 0. So all of the ones involving sine are going to end up being 0. F prime of 0, well, the cosine of 0 is 1. So all those involving the cosine are going to come out to be either 1 or negative 1. So the second derivative is 0. The third derivative is going to be, in this case, negative 1. The fourth derivative is going to be 0. And finally, the fifth derivative is going to be positive 1. And so when I start plugging everything in, I am going to get on this one, the p sub 5 of x is going to be 0 plus 1 times x plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x cubed plus 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth. Which, when I simplify that, I'm going to get p, the fifth derivative polynomial, Maclaurin polynomial, of x is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And that would be our fifth degree Maclaurin polynomial for sine of x. Again, pause the video. Make sure you're comfortable with the calculations I did to get to this point. All right, so now we've gone through and found these polynomial approximations for these functions. How do I use them? Well, really what we're doing, the idea here is that in terms of working with natural log sine or working with a polynomial, the calculations are generally going to be easier with a polynomial than to work with one of the transcendental functions. It's like natural log sine, cosine, tangent, so forth. So what we want to do, we can use our polynomials to go and approximate the value of a function at a particular, for a particular point. So in this case, what we have, I just went through and rewrote the third degree Taylor polynomial for natural log centered at x equals 1. This is the one we developed earlier. And we have it. We know that's approximately equal to the natural log. And in this case, what I want to do is I want to approximate the value of the natural log of 1.5 or 3/2 or 1.5, however you want to look at it. So what I can do is I can take 1.5, put it in for x, put in for the x's. So I get p sub 3 of 1.5 is going to be 1.5 minus 1 minus 1.5 minus 1 squared over 2 plus 1.5 minus 1 cubed over 3. When I simplify that, that gives me 0.5 minus 0.5 squared over 2 plus 0.5 cubed over 3. Now, I did use decimals here, and I am switching to fractions, mainly because the fractions themselves are going to be easier to work with and calculation-wise. And so that's why I went to there instead of going through. I probably should have started out with 3/2. But in this case, when this is going to be 1/2, 0.5 squared over 2 is going to be minus 1/8, and 0.5 cubed is 1/8 divided by 3 is going to be the same as 1/8 times 1/3, which would be plus 1/24. And so when I get the common denominator, I go through and I get 5 over 12. So I know in this case, the natural log of 1.5 is approximately equal to 5 over 12. Okay. Now I would want, under normal conditions on this one, I could go through and put it as a decimal just because this it is an approximation. So this is a very good approximation, but it is just an approximation. And so you should not confuse the fact that it's a fraction here with thinking that that is the exact value. It is an approximate value. So I can say that the natural log of 1.5 is about equal to 5 over 12. The issue with it is that this is an approximation, so there is a difference. That if I take the absolute value, if I was to go through on this and take the absolute value of the actual value of the natural log of 1.5, and I was to subtract 5 over 12, that is going to give me a remainder. And in this case, it would be called the remainder sub 3, the third degree remainder. Okay, and this is the value here that if I added it to 5/12, add or subtracted 5/12, would give me the natural log of 1.5. That the true value of the natural log of 1.5 is the 5/12 plus or minus that R3. Okay, now the trick is, what can we do? How can we go through and find R3? And the answer to that is what's called Taylor's theorem, or if you've been through BC calculus in high school, it's also called the Lagrange form of the remainder. Not sure why you have the two different names. You just do. But what this says is if a function f is differentiable through order n plus 1, you've got to be able to take the next derivative, one more. So like if you're using a 5th degree polynomial for a function, there has to be a 6th derivative in order to go through and use this theorem. That's the idea. Through order n plus 1. In an interval I containing c, then for each x in I, there exists a number z between x and c such that f of x equals f of c plus f prime of c times x minus c. So you'll see that Taylor polynomial centered at c plus r sub n of x. And r sub n of x is equal to the n plus first derivative of f evaluated at z over n plus 1 factorial times x minus c to the n plus 1 power. So this thing looks a little bit confusing, but really it amounts to really going through and doing what would amount to the next term, except you're evaluating the derivative at a different location. It's not going to be at C. Okay, you're evaluating a derivative at some other location, but that number that you're using is going to be a value between x and c. Whatever x is. So if you're working with, if you're centering it at 5 and x is 2, then the value of z is going to be some number between 2 and 5. In terms of getting that particular correct answer. Now, the other issue you have with this is this. For each x in I, there exists a z. Okay? So, the thing that you have in this one is each x can have a different value of z. So going through and finding that particular value of z for your particular x is really not possible. And so with that, what we do is one of the consequences of this is that we can say that the absolute value of r sub n of x is going to be less than or equal to x minus c to the n plus 1 over n plus 1 factorial times the maximum of the nth derivative, the n plus first derivative of f evaluated at z, where z is a number between x and c. It is, in other words, we are looking at what is going to be the maximum of this. Now, the first thing I want you to recognize on this one is that this expression here and this are basically the same. The difference is we took what was in the numerator here, we moved it out in front, we took what was here, put it up in the numerator. Okay, so that's where this over that. The only other difference is we're going to go through, because the remainder is equal to this, we want to find an upper, and we can't specifically say what that remainder is. We want to find an upper bound for that remainder, and that's why we're going to use the maximum of our nth derivative, our n plus first derivative of f evaluated at z. The maximum of that n plus first derivative on our interval from x to c, whatever x is to c. Okay, take a minute, pause the video here, make sure you're comfortable with this, identify any questions you have, and once you are, let's move on to an example and how we're going to use one of the ways we can use this particular use this particular theorem to work with a problem. Okay, so earlier in the video, we went through and we approximated the natural log of 1.5 using our third degree Taylor polynomial centered at 1 to be 5 over 12, 5/12. And so what we want to do here is we want to go through, identify what is the upper bound of our remainder? How much error do we have? How much error do we have in this particular problem? Okay, so to do that, I want you to remember that from what we saw before, that our error, in this case, the absolute value, in this case of R3, is going to be less than or equal to x minus 1 to the 4th power over 4 factorial times the maximum of the 4th derivative of f evaluated at z, where z, in this case, z is going to be between c, which is 1, and x, which is 1.5. Okay, so what I did on this one is I went through and calculated my derivatives. Okay, now sometimes depending on the problem, this one's a little bit easier because I only had to go to the 4th derivative, and I can get to the 4th derivative, and I can see that 4th derivative working our way through is going to be negative 6 over x to the 4th. Okay, and so on this particular problem though, sometimes it might be better, it might be more helpful to go through, especially if it's a higher degree polynomial, to go through and get the general form of that derivative. So in this case, if I was going to look at this, the nth derivative on this particular problem, let's just kind of take a look at that, pause for it. We'll come back to this problem here for a second, but the nth derivative on this is going to be, you'll notice that the first derivative is a positive 1, the second derivative has a negative, third derivative is positive, fourth derivative negative. So it's going to be negative 1 to the n plus 1 power times, if you look at the numerator, so I have 1, when the first derivative is 1, the second derivative is 1, third derivative is 2, fourth derivative is 3. When you see 1, 1, 2, 6, that right there should start maybe thinking factorial. But with the first derivative, when n is 1 here, I'm getting 0 factorial. When n is 2, I'm getting 1 factorial. When n is 3, I'm getting 2 factorial. When n is 4, I'm getting 3 factorial. So it's going to be, in this case, n minus 1 factorial over x to the n. So the n plus first derivative of x is going to be negative 1 to the n times, we got our n plus 2, times n factorial over x to the n plus 1. That would end up being that general form. So I could end up using this. Now, I had n plus 2. I could use just n on that one because n plus 2, negative 1 to the n plus 2, and negative 1 to the n would end up being the same thing. So that's my general form. But for our purposes on this one, I don't really need to worry about that. So in this case, I know we already have that R3 is going to be less than or equal to, that absolute value is going to be less than or equal to x minus 1 to the fourth over 4 factorial times the maximum of my fourth derivative of f evaluated at some number z between 1 and 1.5. So in this case, that is going to be, so for this problem, I have the absolute value of R3 is going to be less than or equal to, because I used, it was going to be, I put in x was 1.5, so it's going to be 1.5 minus 1 to the fourth over 4 factorial times the maximum of, basically it's going to be the absolute value of negative 6 over x to the fourth, or of z to the fourth, sorry, on that problem. So that's going to end up equaling 0.5 to the fourth power over 4 factorial times, well, now we have to take a look. What is going to be the maximum? What value between 1 and 1.5, and we could use the endpoints as well, is going to make this the largest possible thing that it could be, this portion right there? And the answer on that is going to be when x is 1. Because all other z values are bigger than 1. So if I put a number bigger than 1 here, it's going to make this fraction smaller. So the maximum that I could have on this one, this maximum here, is going to be 6. And so 1/2 to the fourth, I can go through, I'm just going to write that as 1 over 16 over 4 factorial times 6. Well, 6 is going to go into 4 factorial 4 times, so this is going to be 1 over 16 all over 4, which comes out to be 1 over 64. So my error on this is 1 over 64. Now the other thing then, what this tells me, is that the natural log of 1.5, I can now say that the natural log of 1.5 is going to be between two values. The natural log of 1.5 is going to be between 5 over 12 minus 1 over 64 and that's going to be less than 5 over 12 plus 1 over 64. And that would be my interval that I would have, that the true value for the natural log of 1.5 is going to be between those two values. Okay. So with this does conclude our video dealing with Taylor polynomials. We will also remind me in class to do an example of another type of problem you could use with Taylor's theorem here, in terms of how far do you have to go to get it, where you're getting a required accuracy, what degree polynomial do I need to use to get that required accuracy. So with that, again, make sure you note any questions that you have. And with that, we will see you in our next class.